In this video, we are going to start looking at logarithms. This is really just an introduction to the idea of logarithms. We will have other videos where we look at graphing of logarithms and some laws of logarithms and all kinds of things, but this one is just going to get us started. And we're going to start off here with the definition of logarithms. You'll see it right here on our first line. Log base b of x equals y. That's a logarithm if and only if b to the y equals x. These two equations that we have right here are equivalent. They are equivalent, and the one on the left, this is what we call the logarithmic form. And the one we have on the right over here, this is what we call our exponential form. Okay, notice both equations have a b. Those will be the same number. B has to be a positive, real number, and it cannot be equal to 1, and we will call that the base. When we talk about logarithms, we talk about their base. It's written as a little subscript down below. And when we have an exponential form, we talk about a base. That's the thing with the exponent on it. Both of these equations have an x, and it's the same x, and there is a restriction. X has to be greater than 0. That is the argument of our logarithm. It's what we're taking the log of. We'll talk more about this restriction when we look at the graphing and talk about domain and range, but for now we just need to remember that x always has to be greater than 0. And then our final variable up here is y, and the y is the answer to the logarithm. It's the exponent in exponential form. Again, those are the same y's, and y can be any real number. We're going to refer to that value as our exponent. So for our first little activity here, we're just going to go back and forth between those two forms. In the column on the left here, I have 3 different logarithmic equations, and I want to convert each one into its exponential form. So this little subscript, that's what we call our base, and that will become the base in our exponential form. The answer to the logarithm, the result, that becomes your exponent, and the argument to the logarithm becomes your result for your exponential. So once you memorize that pattern, these become pretty quick and easy. Again, 5, that's your subscript, that's your base. The answer, the result of the logarithm, is your exponent, and then your argument becomes the result in your exponential version. Okay, we can do it too if there are variables. It still works the same way. The little subscript 6, that's our base. The answer 3, that becomes our exponent, and we set that equal to the argument. And this is one that we could actually go on to solve from here, but right now we're just converting forms. Okay, now on this right-hand column we have 3 different exponential statements, exponential equations, and we are going to rewrite them into logarithmic form. Okay, so again, 6 is your base because it has the exponent on it. So when we write that as a log, that becomes the small subscript. We call that our base. The exponent is going to become our answer, so that's going to go over here on the right. And 36 is the argument of your logarithm. Same pattern on the next one. The 5 that has an exponent on it, that becomes your base, or the little subscript. The exponent, that's going to end up being our answer, and 625 becomes the argument of our log. And the last one, 4 is our base this time, so that becomes the base of our logarithm, our little subscript. That exponent, 2x minus 1, that's going to become our answer, and 64 becomes the argument of our logarithm. We have a couple common logarithms that you will see. Anytime you see just a plain old log x without a subscript or without a base, that automatically implies that the base is equal to 10. Okay, so when you see that log button on your calculator, that is really a log base 10 of x. And similarly, you might have seen on your calculator at some point this ln, that stands for natural logarithm. And anytime you see ln of x, that's the exact same thing as log base e. And again, that's a button on your calculator. And just real quickly, you do want to be careful with your notation on these logarithms. Let's say if you had log base 3 of x. Okay, a logarithm can be written without a base. If it is, then it's log base 10, but it can never be written without an argument. You must always have an argument. And the logarithm and its argument, they are stuck together. Okay, if we have log of x, we can't divide both by x and cancel those. That is not possible. Okay, we don't want to do that. When you have an argument for your logarithm, those two are stuck together unless you rewrite it in its exponential form. Okay, we could also have some statements where we want to evaluate these logarithms numerically. Okay, so we're looking for a number answer here. Log base 4 of 64 is what? And the question we're looking for here is what exponent would we put on that 4 to get 64 as a result? And it turns out that 4 cubed is 64, so this logarithm is equal to 3. Same thing on this next one. Remember, the answer is going to be an exponent. So the question is 7 raised to what power gives me 1 over 49. Okay, well 7 squared would give me 49. If I wanted to turn it into a fraction, it would actually have to be 7 raised to the negative 2 power. This next one, here's our first example of a common logarithm. There's no base, so that really is a log base 10. So to figure that out, we'd take the base and we ask ourselves, what exponent would I have to raise that to in order to get 100 as my answer? And 10 squared is 100, so there's our result. And then this next one is our first natural logarithm. Remember, that's equivalent to saying log base e of e to the 6th. And this is really asking, here's our base, e raised to what power gives me e to the 6th. And when you write it like that, it's almost trivial. Obviously, it needs to be 6. That's our answer. We do have some basic properties of logarithms here. And most of these are pretty easy to see or easily explained. Anytime you have a log, no matter what the base is, if you're taking log of 1, the answer is always 0. And the reason behind that is if we rewrite this in its exponential form, we see that the base raised to the exponent equals 1. And any number we put in here, we know any number raised to the 0 power is 1. So for example, if we had log base 3 of 1, the answer has to be 0. Doesn't matter what number's down here. Log base 7, log base 1000. If we're taking the log of 1, it's always equal to 0. This next one, similarly, if we rewrite this in exponential form, the base, the exponent, and the answer. Of course, a to the first power is a, and that would be true for any base, for any number. So anything we put in down here, log to the 8th, log base 8 of 8 has to be 1. The next one is almost the same. It's just instead of a 1, we could say it could be any exponent. Oh, sorry, we're going to rewrite this in logarithmic form. So the base is a. The answer becomes the exponent. And of course, a to the x is equal to a to the x. So as a sample for this one, if we had log base 7 of 49, well, we already know how to figure that out, but we could rewrite that to demonstrate this property. Log base 7 of 7 squared is equal to 2. And this final one, this one is not quite as easy to explain as the others. So if you want to see the justification behind this one, I'm just going to refer you to your textbook. But for example, to see that applied, if we had 5 raised to the power of log base 5 of 6, if the base is the same here and the same in the logarithm, that is equal to just 6. And we can also solve a couple types of equations with just our starting properties of logarithms. The first type of equation we might see is if we have 2 logs and they each have the same base. So notice that both of these on either side of the equation are log base 6. Because a logarithm is a one-to-one function, we can just take the arguments of the log and set them equal to each other. And then that becomes a nice, quick and easy equation to solve. We'll add that 5 to both sides. We get 2x is 6, or x is equal to 3. Anytime you solve an equation that had logarithms in it, you always need to check your answer. And what we need to check and see, if you remember at the beginning, I said that the argument of a logarithm always has to be positive. We cannot take the log of 0, and we cannot take the log of a negative number. So this expression right here needs to be positive, as does this one right here. So when we plug 3 in there, on the left-hand side, we get 4 times 3 minus 5. 12 times 5, that is positive. We're good to go. If we plug it in on the right-hand side, we get 2 times 3 plus 1. That is also positive, so we're good to go. So this answer does check out. Okay, let's look at another one. Same setup. We've got a logarithm on each side, and they have the same base. So because log is a one-to-one function, we can just take those arguments and set them equal to each other. And again, a pretty easy solve from there. If we bring that 3x over, and I'm going to go ahead and move the 2 at the same time, we get negative 2x equals 9. Divide both sides by that negative 2. We get x equals negative 9 over 2. And then always have to check, because our equation had logs in it to start. We take the argument x minus 2 and we plug in our x value. And I don't even have to calculate what that is. I know that negative 9/2 minus 2 is going to give me a negative answer. So that means that this actually is not a solution to this equation, and instead we have to say that there is no solution. Again, that's because you can't take the log of a negative number or of 0. Okay, those two equations both had 2 logarithms in them. We could also have an equation with a single logarithm. And when we do that, the trick we want to use is to rewrite this logarithm into its exponential form. So we'll take our little subscript, our base. The answer from our logarithm becomes our exponent, and we set that equal to the argument. And you can see, again, once we rewrite it, this becomes a pretty easy equation to solve. 2 to the 5th power is just 32. Add 1 to both sides. We see that x equals 33 is our solution. We go back and check it, make sure when we plug it in right here in our argument, 33 minus 1, that is still a positive number, so we are okay. And that answer works. And our last one, again, there's a fraction here, but it works just the same way. It's a single logarithm, so we're going to rewrite that in exponential form. 8 is our base. 2/3 becomes our exponent. We set that equal to x plus 6. You can do this in a couple different ways. You can probably just plug it in on your calculator, but remember that the 2/3 power, that's the same thing as taking the cube root of 8 and then squaring it. The cube root of 8 is 2, and 2 squared is 4. So to finish up, we just subtract 6. We find out that x is negative 2. And then we have to go back and check. Now, getting a negative number here can be okay for an answer. The really important part is that we can't have a negative value right here. So we have to plug x back in there. We get negative 2 plus 6, and that is equal to a positive 4. So we are okay. This is a good solution.